Now let us discuss about an important theorem. The theorem is known as the characterization theorem. This is very important theorem, that is characterization theorem. The characterization theorem is, that's a very important theorem regarding the intervals. So, the theorem states that if S is a subset of 1, S is a non-empty subset of 1, or S is a subset of 1, that contains at least 2 points. This S is a non-empty subset of 1. So it contains at least 2 points, has the property if x, y fall in S, x, y fall in S, x less than y, then interval xy, closed interval xy, is a part of S, which is an interval. S is xy is a part of S, then S is an interval. So this is the characterization property or characterization theorem. The theorem is very important. If S is a subset of 1 and which has at least 2 elements, so it is non-empty. If x and y are any two distinct elements of S with x less than y, then xy, closed xy is a part of S, then S is an interval. So how to prove this one? So there are so many cases arises. The first one, if S is bounded, there are number of cases. Suppose S is bounded. Bounded means it is both bounded above and below. S is both bounded above and below means S is bounded above means it has a supremum by completeness property. S is bounded below means it has an infimum by completeness property. Since it is bounded means it is bounded above and below, that means its infimum and supremum exist. Let A equals infimum of S and B equals supremum of S. Okay, A equals infimum of S, B equals supremum of S. That means this S is a subset of interval, closed interval AB. How to express an element in closed interval AB? X of all in closed interval AB means X of all in closed interval AB. X of all in closed interval AB means X ranges from where to where? X ranges from A to B. A less than or equals X, less than or equals B. A is infimum of S, B is supremum of S. Surely this S is a part of closed AB. Why? You can consider the set as 1, 2, 3, etc. to 10. What is A? Infimum of S is 1. What is B? Supremum of S, that is here 10. Okay, so clearly S is a part of every element in this S should be present in the closed interval 1, 10. So S is a subset of closed interval 1, 10. Why? Because every element in S is an element of this closed interval 1, 10. So S is a part of 1, 10. Surely, since A is bounded, A is the infimum, so S is bounded, A is the infimum and B is the supremum of that S, then surely S is a part of closed interval AB. Okay. Let us set this as any real number. Set this any real number. Such that set for an open interval AB. What is an open interval AB? If X fall in open interval AB, then means it is A less than X less than B. X lies in between this A and B. So set for in AB means open interval AB means A less than set less than B. Okay, A less than set less than B. Now consider this A less than set. What is A? A is an infimum of S. A is an infimum of S. A is the greatest lower bound. So no number greater than A is a lower bound. No number greater than A is a lower bound. That means Z is not a lower bound. Z is not a lower bound of S. Why? Because A is the greatest lower bound. No number greater than A is a lower bound. Here Z is greater than A, so Z is not a lower bound of S. Since it is not a lower bound of S, then we can immediately conclude that there exists some x following S such that A less than x less than z. Means if z is not an upper lower bound with a z greater than A, then there we can find out an element in S in between this A and z. So A less than x less than z. Okay. Again, now consider this one, z less than b. Z less than b. What is b? B is the supremum, least upper bound. No element less than this b is an upper bound. So that means z is not an upper bound. Z is not an upper bound of S. So then by the same argument we can find out some y following S such that this y following S such that this z less than y less than b. We can find out an element. We can find out an element in between this z and b. Okay. So consider these two arguments: a less than x less than z and z less than y less than b. So we can combinedly we can say that x less than z less than y. Here x less than z, but that z less than y. So x less than z less than y for all x comma y falling x and y is chosen from where? X comma y is chosen from yes. So x less than z less than z lies in between x and y means by the definition of open interval z fall in open interval xy. Z fall in open interval xy. But what is open interval xy? Open interval xy is a part of S. Okay, open interval xy is a part of S. Why? Because x and y chosen from where? S itself. So open interval xy is a part of S. X and y is the distinct element of S. So its open interval surely presents in where? S itself. So subset of S. Z fall in, that means Z fall in S. Z fall in yes. Z is chosen from where? Open interval AB. So clearly this open interval AB is a part of S. Every element in open interval AB should be fallen yes. That means open interval AB is a subset of S. Okay. Then here, if A and B presents in S, means if its infimum and supremum are S itself, in S itself, then what you get? Then S is closed interval AB. Okay. If A and B, if A comma B presents in S, then S equals closed interval AB. Why? Because AB is a part of S, but S is a part of B. Here S is a part of closed AB and the open interval AB is a part of S. Combines these two results. If A and B fall in S, then clearly closed interval AB is a part of S. But we also say that S is a part of closed AB, then clearly S is this closed interval AB. Okay. If A fall in S and B is outside of S, A fall in S and B is outside of S, then S equals closed open AB. B is outside of S. Okay. If A is outside of S and B fall in S, then by using that argument also S is a part of closed AB and then here S equals closed open closed AB. The last case is if A and B are outside of S. A and B are outside of S, then S equals open interval AB. Okay. So clearly in all of these cases S is an interval. S is closed interval AB, open closed AB, closed open AB and open interval AB. So clearly S is an interval here. So this is the first case when S is bounded. So first we prove that if S is bounded, then S is an interval. Okay. Then come to the next case. That is S is bounded above but not below. S is bounded above. Next case, S is bounded above and not below, but not below. S is bounded above but not below. Bounded above means its supremum should be exist. So supremum by the completeness property, supremum exists. Let B equals supremum of S. but which is not bounded below means it has no lower bounds. Okay, no lower bound, so there is no infimum. So, since B equals supremum of S and it has no lower bounds, means it is not bounded below, it has no lower bound, so that means this S is a part of minus closed open, sorry, open closed minus infinity B. Listen, here suppose S equals set of etc. minus 1, 0, 1, 2, 3, etc. to 10. Here 10 is the least upper bound. And all the elements about 10 are upper bounds, but 10 is the least upper bounds. But here which has no lower bounds. Why? Because it is from where to where? It is from minus infinity to that one, which has no lower bound. Surely S is a subset of where? S is a subset of open closed minus infinity B. Clear? When S is a supremum, so S is a subset of minus infinity B. Now, let set fall in open closed minus infinity B. That means set strictly less than B. But what is B? B is the supremum of S. B be the supremum of S and no element less than B is an upper bound. That means Z is not an upper bound of S. Z is not an upper bound of S. Z is not an upper bound of S means there exists an element Y fallen. Z is not an upper bound means there exists an element Y fallen S such that this X Z less than, there exists an element in between this Z and Y, so Z less than Y less than B. Z less than Y less than B. And S is not bounded below. S is not bounded below means this Z is not a lower bound. Z is not a lower bound. Z is not a lower bound of S means there exists an element X falling S such that X less than Z. Yes, it is since Z is not a lower bound, then there exists an element X. You can find out an element X such that X less than Z. Why? Since there is no lower bounds or infimum, so there is no second inequality. So X less than Z means X less than Z, Z less than Y. That means X less than Z less than Y implies Z falling open interval XY. Okay, but open interval XY. What is open interval XY? That's a part of S by the choice of this X and Y. So yes, open interval, but Z is chosen from where? Z is chosen from minus infinity B. That means open interval minus infinity B is a part of S. But S is a part of minus infinity B. That means what is that means S equals open interval minus infinity, open closed minus infinity B. If B fall in S, if B fall in S. There is case if B is outside of S. If B is outside of S, then S equals open interval minus infinity. Clearly, in either of this case, S is an interval. That's our final requirement. This S become or S is an interval. Okay. So this is the second case. And consider the next case. What is the next case? If S is, the second case is S is bounded above and below. The next case is, suppose S is not bounded above, but it is bounded below. Not bounded above, but bounded below. Not bounded above means it has no upper bound, but it is bounded below means it has an infimum. So since S is bounded below means infimum of S exists. Let infimum of S equals A. Okay, let infimum of S equals A. Means here S is a part of S, it is A closed open A infinity. Okay, why? Because infimum it has a lower bound but no upper bound. So this S is a part of closed open A infinity. S is a part of closed open A infinity means, so let us set the following closed open A infinity. What happens? Surely this Z S A less than Z. A less than Z means Z greater than A. Z greater than A, and what is A? Z greater than A, and what is A? A is the infimum of S. So no number greater than z is a lower bound, since a is the greatest lower bound, therefore z is not a lower bound. Z is not a lower bound of S. Z is not a lower bound of S means there exists x of all in S such that this x less than such. X less than such. Then, or a less than, S A is an infimum, therefore it is a less than x less than such. Why? Because since it is not a lower bound of S and S has an infimum that will be A, then since it is not a lower bound, there exists an element lies in between this A and such, means you can find out an element in between A and such, let it be x. So it is A less than x less than such. And S is not bounded above, means it has not upper bound. So it has not, S has no upper bound, means Z is not an upper bound of S. Since S has no upper bound, so this Z never become an upper bound of S. Z is not an upper bound of S means you can find out an element Y falling Z such that this S, you can find out an element in between this Z and its upper bound, so it is Z less than Y. There exists a Y falling Z such that Z less than Y for all Y falling S. So combines x less than Z but Z less than Y, that means x less than Z less than Y, that means Z falling open interval xy, but by the choice of xy it is a part of S. So means Z falling S, but Z is chosen from where? Z is chosen from closed open A infinity, that means closed open A infinity is a part of S. S is a part of closed open A infinity is a part of S, that means S equals closed open A infinity if A fall in S, equals open interval A infinity if A is outside of S. In both of these cases, S is an integer. So clearly, in this case, also we prove S is an integer. Okay. Now, so there are three cases. We have already discussed about these three cases. What is the first case is S is bounded. Second case is bounded above but not below. Third case is S is bounded below but not bounded above. And the last case is S is not bounded above and not bounded below. Which is not bounded means S is an unbounded set. S is unbounded, not bounded below and not bounded above. There is no boundedness property. So, let's set the following number. Set is any real number. And what it says? S is a subset of 1. Clearly, this set is not an upper bound of 1. Set is not an upper bound of 1. Sorry, upper bound of S. Why? Because set is, since S is not bounded above. Z is not an upper bound of S means there exists an element Y falling S such that what do you get? Yes, it is Z less than Y or Y is Z less than Y. Okay, since Z is not an upper bound, there exists a Y falling S such that Z less than Y. Z is also not a lower bound. Z is not a lower bound of S. Means there exists an element x falling S such that x less than such. So combines Z less than Y, x less than such means x less than Z less than Y. That means Z falling where? Open interval xy, which is a part of S. Okay. So R is, but Z is chosen from where? Z is chosen from R. That means R is a part of S. But what is S? S is a part of R. S is a part of R. Combines S equals R. S is a part of R. R is a part of S. S equals R. What is R? R means open interval minus infinity, infinity. This is a real line. Minus infinity to infinity. This is R. So real line. So S equals R. Minus infinity, infinity. What is minus infinity, infinity? Which is nothing but an integer. So this is our requirement. So in either case, in any case, if S is a non-empty set and S is a, you can find out any two elements, at least two elements in S, which is X and Y such that X less than Y, then this S is nothing but an integer. That is the characterization theorem. This characterization theorem is an important result as well as it is an interesting result. So there are 4 cases. S is bounded, that is first case. Second case is bounded above but not below. Third case is bounded below but not above. And fourth case is S is neither bounded, means it is neither bounded above nor bounded below. So here Z is chosen from where? R. S is a part of R, Z is chosen from R. Since Z is not an upper bound, by this property Z greater than 5. Z is not a lower bound, there is a property X less than Z. Okay, so combined we will have this result. Agree? Thank you.